Good afternoon, everyone. Today I'll be presenting our work Vindicator, a new sound online predictive analysis capable of detecting a larger set of data races than prior online and offline approaches. It can do so within reasonable time and space and maintain scalability to large programs. Okay, now you can hear me. As you may all know, data races are bad, and more generally, concurrency bugs are a difficult issue to address in programming. This is due to the non-deterministic behavior of parallel programs and allows data races to manifest in unintended or unintuitive ways. This can cause millions of dollars in damages and in some cases even claiming lives. Now more than ever, data race detectors are important due to the rising popularity of parallel programs. And correctness is even more important to guarantee since common memory models such as C++ and Java provide undefined or ill-defined semantics for data races in them. And so what do we do about data races? How can we handle them to avoid situations such as these and guarantee that our programs are correct the way we intend? The most prominent type of race detection, dynamic analysis, and commonly associated work such as Fast Track, Thread Sanitizer, or Intel's Inspector, which are industry standards, detect data races by evaluating a single execution of a program. But unfortunately, in order to detect all such races within a program, thousands or millions of iterations would have to be executed in order to find all such races. And so ultimately, these techniques are limited to a subset of the total races that still exist. So let me introduce to you an example in order to showcase how dynamic analysis, or more specifically in this case, happens before analysis detects races from a single execution. So in this single execution of a program, which is read from top to bottom in observed order, we have two threads executing a series of events, which can be a read or write to some shared variable or acquire release to some lock. Note here that the two accesses to X remain unprotected by synchronization. At least one of them was a write, and they're accessed by two threads. So some interleaving of this program allowed the two accesses to execute concurrently, meaning no interleaved other events. Then a data race would manifest, and the rest of the execution would remain undefined. Happens before analysis detects races from a single execution by ordering events using a set of rules. It does so by ordering events of the same thread in the observed order, and so the write of X is ordered before the acquire M. Critical sections of the same lock are ordered from release to acquire, and happens before, lastly, is transitive. In this case, it means that the write of X is ordered before the read of X. And so no race is detected. But let me ask you, in this example, from the single execution, does a data race exist in this program? Yeah, okay. The answer is yes. If thread 2 were to execute the critical section on M first, then the two conflicting accesses would be allowed to execute concurrently, thus a data race could be detected. So how do we overcome the limitation of happens before analysis? Can we simply do away with the orderings established between critical sections? Predictive analysis attempts to do this, but it must do so in an intelligent way, not to report any false positives. Here we have a different program in which the two critical sections of the same lock now execute a shared common variable z. Note here that the read of z depends on what value has been written to it by thread 1. And so any control flow that may be dependent on the value read by z in thread 2 could dictate whether the read of x ever executes or not. And so let's do something crazy and reason about an alternative interleaving of these events without actually executing this series of events, meaning we don't have the dynamic information of this execution. We only know that the read of z must see the value that has been written to it in thread 1 in order to know what happens for the rest of the execution. Now we're unsure of exactly which events will be executed if there's any control flow dependency on z. If a race were to be reported, this would be considered a false race since we're not guaranteed to know that the two events could execute concurrently. So predictive analysis must order critical sections in some manner, but what's the limitation? Do we have to order anything that has accesses within it? Take a different program which is slightly different from the prior example, in which the read of z is now a read of y in thread 2. And so these two critical sections of the same lock now access different shared variables. And so if we were to reorder the two critical sections, we're guaranteed that the same events would execute given the dynamic information from this single execution. Thus, predictive analysis could detect that a race exists between the shared variable on X. And so predictive analysis and recent prior work we call supersedes, which supersedes recent prior work called supersedes, does just this. Both approaches weaken the happens before relation in order to reduce the orderings between events, so that way a larger set of races can be detected from a single execution. Unfortunately, in order for these approaches to report only true races, they left and right compose with the happens before relation and ultimately end up missing races that exist within a program. Alternatively, SMT-based approaches combine constraint solving with dynamic information from a single execution in order to report all such races that exist within a program from a single execution. But unfortunately, due to the complexity of these approaches, they're unable to scale to large real-world programs and thus ultimately miss races that still exist. On the other hand, our approach Vindicator is able to detect a larger set of races than prior work and maintain scalability to large programs. So let me introduce to you let me show you an overview of how our approach works. Vindicator first takes a program execution and analyzes it using a new doesn't commute relation. The relation orders events, and any two events that remain unordered are considered a race. These are stored in a table during the analysis. In addition to detecting races, Vindicator also builds a constraint graph during analysis in which the nodes correspond to the events of the original execution and edges correspond to the relations established between events during the doesn't commute analysis. And so highlighted in yellow, we have two events that have established some relation between them, and this is reflected within the constraint graph. Now, DC detects races, but it not only detects true, but false races as well. And in order for Vindicator to avoid reporting false races, the second contribution, Vindicate Race, is used to evaluate every DC race that has been detected and build a feasible alternative interleaving that can witness a race to determine if it is true or not. And so our approach Vindicator detects and verifies races that prior approaches are unable to detect. It maintains scalability, and our initial implementation is efficient enough to verify races in time and space for heavyweight testing. And so in order to help you better understand how our relation doesn't commute detects races from a single execution, let me introduce to you another example in which a race does exist between the shared variable on X. DC detects races by ordering events and does so using a set of rules. So any event within the same thread is ordered due to the observed order. In this case, the right of X is ordered before the acquire M. These are omitted due to simplicity. DC is also transitive. Both of these rules are similar to the happens before relation, but different to HB, critical sections of the same lock must access the same shared variable and are ordered from the release to the second shared variable instead of a release to acquire. This rule is the same as recent prior work we call supersedes, or WCP in this case. But different to DC, we call supersedes also left and right composes with HB. And so in this example, the two critical sections on N are happens before ordered, and this composes with WCP to ultimately order the right of X to the read of X, thus missing the simple race within this example. On the other hand, the doesn't commute relation avoids composition with HB, and thus is able to detect the race on X in this example. That's all great, but unfortunately, DC also reports false races, as I mentioned before. And so in order to avoid this, as I was saying, the Vindicate Race contribution attempts to build a feasible interleaving of events that can expose a race, so that way we have a witness that says the race is true. Here we have an example showcasing this fact. Let me mention first that I have summarized events that are a critical section accessing a shared variable in order to fit the example on screen while still establishing the relations needed. Observed order and transitivity are omitted due to simplicity, but as you can see, between the two axes on X, which are the perceived data arrays, remain unordered by the DC relation. And so DC reports that a race exists. But unfortunately, no interleaving is possible for this program that allows the two accesses to execute concurrently. Thus, no data race does actually exist. And so coming back to the overview of Vindicator, so far we have seen that Vindicator has analyzed a program execution using the doesn't commute relation and it is now left with a table of DC races, which may or may not be true, and a constraint graph in which the nodes correspond to the events of the original execution, and edges correspond to the relations established between those events. Now, Vindicate Race takes each individual DC race and attempts to build a feasible alternative interleaving using the constraint graph in order to expose the race if it is a true race. To better understand this, let's dive a little bit deeper into Vindicate Race, in which the first step is to add any missing constraints to the initial constraint graph. So coming back to this example here, we can see that the initial constraint graph is exactly the events and the relations established between them as shown on screen. Any missing conflicting access, any missing constraint must be added back in order to expose the race on X, since the initial constraint graph is insufficient for determining whether a race is a true race or not. Otherwise, DC would only report true races and vindication would be unnecessary. The intention of adding a constraint within a constraint graph is in order to enforce that the two conflicting accesses execute concurrently. And so any event ordered before the write of X must be constrained before the read of X, and any event ordered before the read of X must be constrained before the write of X. This enforces that a reordering of these events will force the two conflicting events to execute concurrently, thus hoping to expose a race. Any additional missing constraints are between critical sections, since the doesn't commute relation avoids composition with HB. In order for Vindicate Race to determine whether a pair of critical sections need to add a constraint between them or not, a later critical section must have a path to an earlier critical section through the set of constraints in the constraint graph. And so as example here, the acquire M in thread 2 has a path of constraints all the way up to the release M in thread 1. And so for a reordered execution, to satisfy this path of constraints, the entirety of the critical section in thread 2 must execute before the entirety of the critical section in thread 1. And so a constraint is added from the release M to the acquire M. Once a fully constructed constraint graph has been finalized, Vindicate Race can then attempt to build this feasible interleaving that exposes the race. But in this example, as you can see, the non-grayed out elements, if we attempted to reorder them, one of the two constraints would be violated. And so no feasible interleaving could possibly exist for the accesses on X. And so coming back to this overview, Vindicate Race will fully construct a constraint graph and then first attempt to check if a cycle exists within this graph or not. If the graph remains cyclic, then no race is reported. Otherwise, if it remains cyclic, then Vindicate Race can attempt to construct the reordering. And so imagine a different example in which a data race does exist that DC has detected. The fully constructed constraint graph would then remain acyclic, and Vindicate Race could attempt to construct this reordering. It does so by taking the two conflicting accesses and executing them concurrently. And then in a greedy approach, it builds the reordered execution from bottom up by taking the latest event in the observed order that is both necessary and its constraints have been satisfied. A necessary event is one in which it is reachable to either conflicting access. If these conditions are satisfied, it is added to the reordered execution. And if successful, if all events that need to be added are added, a witness to a true race has been constructed, and so Vindicate Race has verified that this is a true race. An interleaving exists that exposes the race. Otherwise, if Vindicate Race is unsuccessful in constructing this alternative feasible interleaving, Vindicator simply reports don't know. This is due to the use of a greedy approach, and more details are in the paper. So now that I've shown you that how Vindicator is able to detect and verify races using the doesn't commute relation, how many races is it able to report that prior work has remained unable to report? And what is the performance cost of the analysis and the vindication process? Is it worth finding these races? Vindicator has been implemented in Roadrunner and evaluated against a set of capo benchmarks on a quiet 14-core Intel Xeon. The results are averaged over 10 trials. And in addition to the DC analysis, the prior work we call the precede analysis and an HB analysis have also been implemented in Roadrunner. The left-hand side of all the major columns show the number of races. The left-hand side are the static races, which are pairs of unique locations, and the right-hand side are the dynamic instances of each static race detected. Note that the set of happens before races are a subset of the WCP races. Of the 63 races detected by the WCP analysis, 59 of them have remained undetected by the happens before analysis. This is similar for the DC analysis. The set of HB and the set of WCP races are both subsets of the total DC races that have been detected. And so the 67 races the DC analysis have detected, 4 of those races are undetected by WCP or HB. Of the DC races detected, all dynamic instances of the DC-only races have been successfully vindicated. This means that Vindicate Race has been able to construct a feasible alternative interleaving that exposes the race. DC-only races are races that are not HB or WCP, since these are guaranteed to be true. Now that I've shown you that Vindicator is able to detect a larger set of races than prior approaches, what is the performance cost of the analysis and of the vindication process? As mentioned, WCP analysis has also been implemented in Roadrunner, and the slowdowns are in comparison to the native execution of the benchmarks averaged over 10 trials. To remind you, Vindicator is not only implementing the DC analysis and the constraint graph construction, but we've also included the WCP analysis for a fair comparison of race results. And so the slowdowns are within reasonable bounds for heavyweight testing and very comparable to prior work. In addition to the analysis times, we've also collected the average vindication time. This is the amount of time taken to vindicate a single race. The numbers are calculated by the total amount of time to vindicate all dynamic races for each benchmark divided by the total number of dynamic instances for those benchmarks. The range of vindicating a single race goes from anywhere from less than a millisecond all the way up to 4 seconds. This variation is due to the fact that a different number of constraints must be added per race. And so in conclusion, our approach Vindicator detects and verifies races that prior work is unable to detect. It maintains scalability to large programs and is able to detect races that are millions of events apart. And our initial implementation is efficient enough to verify races within time and space for heavyweight testing. Thank you. Any questions?
Questions? Hi, thanks. I think it's fascinating to see more progress in this space. One thing I was curious about is with the detection evaluation, with happens before, you run it just once, and then, or you're running happens before multiple times?
So you're asking about this slide?
Yeah, that's right.
Okay, so for all 3 analyses, they've all been implemented to work on the same trace. So we run the program once, all 3 analyses do their thing, they all give us a set of races, and then we did 10 trials of this in order to collect the results.
Okay, so it's apples to apples. I'm curious about how much happens before gains from how much total coverage do you get if you have, say, 2 runs of happens before versus 2 runs of DC? Have you done that experiment at all?
I guess not specifically, but in this case, it would show that after 10 trials, the number of HB races detected is significantly smaller than what prior work has detected, and even after 10 trials, prior work couldn't detect some of the races DC was able to detect.
Sure. Okay, thanks.
Yep.
Hi, nice work. You mentioned that, actually on this slide, you were able to vindicate all of the races,
yes.
All of the DC races in Da Capo, but yet there's still this possible don't know outcome for the vindication process. Do you have any experience beyond these benchmarks or in other scenarios where you've actually encountered the don't know in practice?
Yeah, so don't know comes from the fact that we use the greedy approach when building a feasible interleaving that can expose the race. And in our extended tech report, we go into detail about what other methods could be used if don't know comes up. And we do have examples, there's small examples that show, like, yes, latest ordering would be incorrect in this case, and you'd miss the race when you shouldn't. And then if we use a random approach, that can also result in the same thing. So there's not one, overall best solution, but we give it our best effort, and so far we haven't found it to be a problem.
And it's just small examples.
Yeah, they're just
so
small
you haven't
examples
actually
so
seen
far.
it in the wild.
Yeah, not
Cool.
in one.
Thanks.
Yeah, no problem.
Any more questions? Okay, thank you.
Mhm.